we're going to see another example on this, and we have this car, and we have the diagram, and based on what we have learned about the diagrams, um, the motion is different from the first 10 seconds than it is for between 10 and 30 seconds. So we have to take it like individual sections and apply the individual equations. So let's see how we're going to do this. Alright, in this case you're giving the velocity versus time diagram, and the question is, can you find the acceleration versus time diagram, the average speed, and distance traveled for the 30-second interval? Okay, so very simple questions, but very important ones. So how we would go about doing this? The plan would be to find the slopes of the curves and draw the velocity versus time diagram. Find the area under the curve would be the distance traveled. And finally, calculate the average speed using the very basic definitions. Okay, very good. Well, let's try that. Between 0 and 10 seconds, the acceleration is going to be dv dt, which is in this case the derivative of that function that you see here. This would be 8t, 0.8t. That would be the acceleration in there. So if this is the plot of the velocity change, the derivative of that dv dt becomes 0.8t. So this is also a line. It is a function of time. 0.8t is a constant change. You have that between 10 seconds and 30 seconds, the acceleration is dv dt. This would be the derivative of this. If the velocity has a line, not a quadratic as in the first 10 seconds, then obviously a is going to be a constant because it's the slope. And in this case, it would be 1 because you see the change would be between 40 and 60, which is 20, divided by the change between 10 and 30, which is also 20. And because this is a line in here, we can do what we just did because of the triangles and other figures that this generates. So we are able to find the acceleration during the other interval too. So if you make a plot, you could see that the acceleration was changing from time 0 up to here, and then it decelerated to a constant acceleration. That's what it means. That's what these two conclusions mean. Okay. But if we want to integrate for the position between 0 and 10, we will do it integrate of the velocity versus time, which would be is basically the area. So this would be 1/3 of 0.4 t cubic. That is this one. That is going to be the area under this curve. Okay, and the position between 10 and 30, the integral of the velocity versus time, which in this case we will have to, we are basically integrating. Let's go see this. We need to make the integration in this interval to know the position. All right. And then between 0 and 30, you have the position. This would be 1000 plus 400 divided by 3, 1133 feet. Okay, so the distance is going to be 133 feet at a velocity average speed of 37.78. Let's see, how do you think of these questions? Slope of a VT graph and any instant represent instantaneous what? Velocity, position is the derivative, right? So what would be the answer here? Obviously B. Displacement of a particle in a given time interval equals the area under the velocity diagram. So this would be the displacement would be the time interval given at equals the area under the, let me see, we answer this would be the VT curve. Okay, well, let's see, if a particle starts from rest and accelerates according to this graph, is the particle's velocity at t equals 20 seconds is what? So what you are giving here is t and you are giving the acceleration. If you are going to do the velocity at t equals to 20 seconds, so during the first triangle there, the velocity would be the area under the curve, right? So what is it? If this is 20 seconds and the other is 10, what will be the velocity right there? Huh? 100. Okay, very good. Anyway, that's enough for this. We move on to other examples.